Welcome back. Electrical Machines Part 4. I repeat, Electrical Machines Part 4. Welcome back. Now, what I'm going to try and do here, let me see if I can do this a little bit. I can highlight this. And, now I want it easy to be read so that you can follow me. So I'm trying to make sure that I can improve on this every occasion I get. Okay, just bear with me for a second while I make sure that I've got what I have in mind done. Okay, let's start my exercise. Okay, welcome back again. Electrical Machines Part 4. Okay, I repeat, Electrical Machines Part 4. And again, we're still looking at NVQ Level 3 electrical installations. Okay. Now I made this slightly larger because I want to be able to emphasize for those of you with bad eyesight like myself, the difference between the speed of the rotor and the synchronous speed of the rotating magnetic field is known as the slip, which can be expressed either as a unit or in percentage terms. Because of this, we often refer to the induction motor as being an asynchronous motor. Remember, the speed of the rotating magnetic field sorry about that. These things are coming at the most peculiar time. Sorry about that. Okay. Because of this, we often refer to the induction motor as being an asynchronous motor. Remember, the speed of the rotating magnetic field is known as the synchronous speed, and this will be determined by the frequency of the supply and the number of pairs of poles within the machine. The speed at which the rotor will turn will be between 2 to 5% slower, with an average of 4% being common. Okay. We already know that when a conductor passes at right angles through a magnetic field, current is induced into the conductor. The direction of the induced current is dependent on the direction of movement of the conductor, and the strength of the current is determined by the speed at which the conductor moves. If the rotating magnetic field and the rotor are now revolving at the same speed, there will be no lines of magnetic flux cutting through the rotor bars, no induced EMF, and consequently no resultant magnetic field around the rotor bars to interact with the rotating magnetic field of the stator, which means that this motor is now stationary. It's not going in anywhere fast. Okay? The motor will immediately slow down, and having slowed down will then start to speed up as the lines of magnetic flux start to cut through the rotor bars again, and so the process would continue. Standard AC induction motors therefore depend on the rotor trying but never quite managing to catch up with the stator's magnetic field. The rotor speed is just slow enough to cause the proper amount of rotor current to flow so that the resulting torque is sufficient to overcome windage and friction losses and drive the load. Okay? Determining synchronous speed and slip. All AC motors are designed with various numbers of magnetic poles. Standard motors have 2, 4, 6 or 8 poles, and these play an important role in determining the synchronous speed of an AC motor. As we said before, the synchronous speed can be determined by the frequency of the supply and the number of pairs of poles within the machine. We can express this relationship with the following formula. Synchronous speed N in revolutions per second equals frequency F in hertz over number of poles per pair. So if you have 2 poles, you have got 1 pair. If you've got 4 poles, you have 2 pairs. Okay? Okay, let me just bring this down to reduce this in size again. So I can. When a conductor passes around, well, yeah, you should know that by now, okay? You can read that for yourself. Thank you. Now here's an example that I want to, let me make sure I can bring this up. Can I bring this up bigger? Just make sure I can bring this up bigger. Can I bring this up bigger? Do I need to bring it up a bit larger, do you think? No? Okay, now. Calculate the synchronous speed of a 4-pole machine connected to a 50 Hz supply. As we know, the motor has 4 poles. This means it has two pole pairs. We can therefore complete the calculation as ns equals 50 over 2, therefore ns equals 25 revolutions per second. To convert revolutions per second into the more commonly used revolutions per minute, simply multiply n by 60. This new value is referred to as ns, which in this example will become 25 times 60, giving 1500 revs per minute. Okay? Now make sure you write this out for yourself, okay? We also said that we refer to the difference between the speed of the rotor and the synchronous speed of the rotating magnetic field as the slip, which can be expressed either as a unit, S, or in percentage terms. We express this relationship with the following formulae. Percentage slip equals synchronous speed, N, minus the rotor speed, NS, minus the rotor speed, NR, over synchronous speed, NS, times 100. So we're looking here at a percentage slip, okay? Examples to note: in this example, numbers have been rounded up for ease. A 6-pole cage induction motor runs at 4% slip. Calculate the motor speed if the supply frequency is 50 Hz. S percent equals NS minus NR over NS times 100. We therefore need first to establish the synchronous speed. As the motor has 6 poles, it will have 3 pole pairs, 3 pairs. Consequently, synchronous speed NS equals F over P, giving us 50, and therefore NS equals 16.7 revs per second. We can now put this value into our formula and then by transposition rearrange the formula to make NR the subject, consequently giving us 4 equals 16.7 minus N over 16.7 times 100. Therefore, by transposition, now I would approach this transposition a little bit different. I would approach it a little bit different, but then again, just my style of learning, okay? So you need to find yours. I'm not going to change anything on here because I think it's important that you find your own method of application and applying these calculations here. Okay, so you can now see that NR was up in here, okay, first, okay? We have to transpose for that. Now for me, I like to show a bit more detail. I would have loved to have seen this up here, times 4 times here, okay, before we got to the 100%. And you can see that's 0.668%, which is equal to 66.8% slip, roughly, if I remember correctly, but don't hold me to it. This is for you to find out for yourselves as well. Okay. Okay, so I was trying to look at it as a percentage. It's okay, just ignore me. I was going away on my own jollies then. Okay. So make sure that you have put this into place. Write it out. Do it. Then your next piece. Therefore, by further translation, you can then see what happened here. It tells you here 0.68 becomes 16.7. Okay. Okay. Right. Let me see. Get you back into frame. Okay. I am in frame. Okay. Where am I? Now, synchronous AC induction motors. A synchronous motor, as the name suggests, runs at synchronous speed. Because of the problems discussed earlier, this type of motor is not self-starting and instead must be brought up to almost synchronous speed by some other means. Okay. Sorry, I keep drifting off from my... That's better. Okay, let me take it off at an angle. Okay. Now, three-phase AC synchronous motors. To understand how the synchronous motor works, assume that we have supplied three-phase AC power to the stator. Now, this one I'm going to leave for you to read through for yourselves. Okay. So it's the gump that keeps cropping up on my computer lately here. Complete gump. Okay, so this one I'm going to leave you to read. Of course, I've read a lot of this already, and it's now becoming somewhat repetitive in its own way. Okay, but it's important for you to be able to know what this is. Okay. You know, when I see a diagram, it tells me so much. It says so much. Because here you have the windings of your motor, and they are connected in delta. Okay, each one has its own phase coming into it. A motor can be manufactured with the windings internally connected. If this is the case and there are 3 terminal connections in the terminal block labeled U, V and W, now be aware of any changes in regards to U, V and W in regards to the real world application. Okay, and again be sure that you are consistent with the IEE regulations. Do not ignore that. It is your responsibility and it is your duty to ensure that you are concurrent with the IEE regulations at all times. Okay. You expect the motor winding to be connected in a delta configuration. This is shown in figure 6.19. So why was I talking about star connection? Sorry, motor winding with delta connections. My apologies. I got carried away there then. Something else. Okay. Right, let me just run this again. Motor winding. A motor can be manufactured with the windings internally connected. If this is the case and there are 3 terminal connections in the terminal block labeled U, V, and W, you would expect the motor winding to be connected in a delta configuration. This is shown in figure 6.19. Okay. I'm going ahead a little bit ahead of myself here then. Okay. Figure 6.19, motor windings with delta connections. Okay. However, there may be 4 connections in the terminal box labeled U, V, W, and N. If this is the case, the winding would be arranged to give a star configuration as shown. Okay. Let me just see what we're saying over here. Okay. Pick that up for you. Okay. Thank you. Okay. Now, I love these diagrams. I do. I really do. Because a diagram tells you so much and it provides you with so much information and the layout as to how it is wired, basically. Alternatively, the terminal block may contain 6 connections. Okay. Which means that you have in this, if it's 6 connection, then you have a star delta connections or supply in that box. I suppose you might need to determine how you're going to link them out, so the option might be used. Sorry. Alternatively, the terminal block may contain 6 connections: U1, U3, V1, V2, W1, and W2. This is used where both star and delta configurations are required. Okay. The terminal connections can then be reconfigured for either star or delta starting within the terminal block. Figure 6.21 illustrates the connections that would come out to the terminal block. Okay. And let's just make sure that you can see this for yourself in full view. Okay. Okay. Just take note what it says about all the motors and bear that in mind. Okay. Motor starters. A practical motor starter has to do more than just switch on the supply. It also has to have provision for automatically disconnecting the motor in the event of overloads or other faults. The overload protective device monitors the current consumption of the motor and is set to a predetermined value that the motor can safely handle. When a condition occurs that exceeds the set value, the overload device opens the motor starter control circuit and the motor is turned off. The overload protection can come in a variety of types, including solid-state electronic devices. Sorry about that. The starter should also prevent automatic restarting should the motor stop because of supply failure. This is called no-fault protection and will be discussed later in this section. Okay. The starter must also provide for the efficient stopping of the motor by the user. Provision for this is made by the connection of remote stop buttons and safety interlock switches where required. Okay. The direct online DOL starter. This is the simplest and cheapest method of starting squirrel cage induction motors. And here we have one, simply to show you. Okay, I don't need to read any further, you can read that for yourselves. Okay, and I believe it should be clear enough. Here's how it's set up as well. Here is your start contacts, pulls in. These are your overload protection of the motor. Any one of these trips out will disconnect the supply to the motor. Okay. And thank you. This is electrical machines, Terence Payne, part 4. Okay. And again, thank you for your time. Let me just make my way up, make sure that I can get everything into play. Let me just reduce the area down to 1. Okay, and let's just make sure we can get everything here that we want to see. Okay.